The AI industry is currently obsessed with a single metric: the size of a language model's working memory. Engineering teams are racing to scale context windows to millions of tokens, so these models can process entire databases in a single prompt. This chart shows the rapid, exponential climb of that token scale. In 2020, we were working with just 2,000 tokens. By 2026, projections push that number past 10 million. The standard assumption driving this race is straightforward. If you provide a model with a massive amount of raw text, its reasoning capabilities and accuracy should naturally scale up in tandem. But the engineering reality tells a different story. Feeding frontier models millions of tokens actually degrades their core understanding and makes their outputs less accurate. This chart shows the phenomenon known as context rot. As the context length stretches, the model's ability to accurately retrieve information collapses. Right at the 128K token mark, accuracy falls off a cliff. Pouring more input does not guarantee better output. To build true AI reasoning, organizations have to abandon this infinite buffer paradigm entirely. Brute forcing massive amounts of flat text into an LLM's memory is financially expensive. More importantly, it is mathematically ineffective for retrieving the accurate, multi-hop answers that complex tasks require. To understand why this memory degradation occurs, we have to look at the underlying mechanics of the LLM architecture itself. The core constraint lies in the transformer architecture, specifically a process called the self-attention mechanism. Self-attention is a mathematical operation that allows a model to weigh the importance of different words in a sequence relative to each other. Because of how the math works, every token in the window must compute its relationship with every other token. This creates the quadratic wall. If you double context size, computational cost quadruples. The industry is deploying methods to stretch the window without hitting that wall: compressive memory like InfiniAttention, state space models like Mamba, and rope scaling. But these scaling methods are temporary fixes. They still rely on maximizing a static block of input. Forcing a system to process a massive, flat file at once is computationally doomed. Processing information at scale requires a segmented, modular approach to memory. The architectural solution involves physically splitting the model's memory. Instead of one massive buffer, the system uses a small, fast short-term window paired with an unbounded long-term storage array. This diagram shows how that virtual memory model works in practice, using frameworks like MemGPT. It separates the main context, acting like RAM, from the archival storage, which holds vectors and cached data. This graphic explicitly crosses out the traditional encyclopedia approach of reading everything. Instead, it highlights the targeted fetch mechanism of Retrieval-Augmented Generation, or RAG, which pulls only the specific data needed. To operate this split virtual memory, you need a specific type of software entity called a Recursive Language Model, or RLM. A standard LLM acts like a stressed speed reader trying to hold a massive stack of books. An RLM acts as an organized librarian. It treats context as a structured environment to explore, not a buffer to fill. It navigates this environment programmatically, using specific tools to find exact answers, instead of relying on brute force memorization. This schematic shows the LLM writing code to an external REPL. A REPL is an interactive programming environment that takes inputs, executes them, and returns the result. The model uses this to run targeted functions like search and partition. Granting an AI the ability to dynamically navigate and fetch information entirely circumvents the cognitive overload and the financial costs associated with the quadratic wall. The ultimate, highly efficient data environment designed specifically for a recursive language model to navigate is the knowledge graph. When you combine these two technologies, you get a powerful architecture known as RLM on KG. This pairing enables the model to perform autonomous, entity-first exploration over highly structured data. This circular diagram maps the 5-step recursive process the model uses to hunt for answers: seed, expand, verify, collect, and re-rank. In the initial discovery phase, the model seeds a query and expands potential paths. Then, during the extraction phase, it iteratively verifies facts and collects specific data chunks. This live navigation node map interface shows what this looks like in real time. The RLM actively pulls in data chunks, moving from node to node based on the logical relationships defined in the graph. This precise, targeted node navigation contrasts sharply with the blunt, linear search mechanics used by standard GraphRAG systems. This benchmark chart displays empirical proof of this architecture's superiority. RLM on KG achieves a higher F1 score, a metric balancing precision and recall. It boasts a 56% win rate when evidence is scattered across 11 or more chunks. Recursive language models will win outright when answers require synthesizing deeply fragmented evidence across a complex, structured system. This engineering architecture has a direct, immediate impact on web strategy and technical SEO. This chart shows AI-generated answers evolving. Across 3 generations, we see a shift from verbose reasoning in GPT-4o to highly efficient relational synthesis in GPT-5.4. Consequently, models stop citing sources, increasingly knowing the answer without explaining how. An inverse relationship is forming. The reasoning density of the output is rising, but brand mentions and outbound links are disappearing. This slide reveals the scale of this new reality, with a massive red 7% ghost citation metric. This means models use your brand's content to generate answers, but actively refuse to give you credit or provide a link back. This box plot proves this lack of citation isn't a glitch. It shows the tight reasoning density distribution of GPT 5.4 across navigational, comparative, and multi-hot buckets. The tight boxes indicate a predictable feature of high reasoning models. Investing in flat text optimized solely to capture traditional AI brand mentions is now a dead business strategy. The models are simply extracting the utility and dropping the attribution. The only viable technical defense against the ghost citation crisis is transitioning your content from human-readable text to agent-readable entities. This diagram traces web markup evolution, starting with archaic flat HTML on the left. The middle step, embedding JSON LD, provides marginal gains if data remains hidden. Finally, enhanced entity pages must be dereferenceable, deeply linked, and structured to be agent-readable. Highly structured data provides the literal track that RLMs navigate to fetch accurate information. Its purpose has shifted from influence-based ranking to machine-level utility. Every organization must now act as its own AI research lab, building bespoke knowledge graphs to survive the transition. Organizations that provide perfectly structured data for autonomous AI will lead the next generation of digital visibility. Dereferenceable accuracy is the true competitive edge, far surpassing the utility of massive context windows.